In the previous example, we were working with a function where there was one independent variable. For example, y is a function of x. And to find the differential dy, quite straightforward, we need to find the derivative of this function here with respect to x, and we would include that here, multiplied by dx. Now we're going to work with a function where we have two independent variables, for example, and in that case, we're going to have two separate treatments of dy, where each dy is a partial with respect to x and w. So that's what we see written here below. You can see we have to work out the effect of a change in x on y as well as a change in w on y. And to do that, we need to take the partial derivative, calculate the partial derivative of this function here with respect to x. We would include that here, times dx, which remember is an infinitesimal change in x, a very, very small change in x. And down here, we are measuring effectively or calculating the change in y due to a change in w. And similarly, to work this out, we would have to partially differentiate this function here with respect to w, and we would include that here, multiplied by dw. We would then need to add both of these together to get the total differential dy in this case, because it's by adding these together that we'd be able to work out the sum of the change in y that occurs from a change in x and w. So as indicated here, we are now finding the differential dy, and we are allowing w and x to change simultaneously at the same time. So we can also interpret these partial derivatives as converters. All right, so if we go back down to this here, we need to think of these as converters, converting the change of, in this case, x and y into changes on z. So if we look at this example here, we can see we're given this function z equals, and we have the variables x and y, independent variables. If you are asked to calculate the differential dz, the total differential, you have to work out not only how a change in x, an infinitesimal change in x, is going to affect z, but also how an infinitesimal change in y will change z, okay? Because x and y in this example are the independent variables. So what we need to do in calculating dz, we need to go back to this function and partially differentiate with respect to x, all right? And that is what you see down here. Okay, so we're partially differentiating with respect to x. So remember, in that case, we are treating the y as a constant, okay, times by dx plus, then we need to partially differentiate this function with respect to y. And that's what we see down here in this bracket. All right, for both calculations here, for partially differentiating here, we are simply using the power function rule, and here as well, because it's the partial derivative of z with respect to y, we are treating x as a constant, okay, and then dy. All right, so that there would be the differential dz, and it's the sum of the change in Z that will occur from a change in X and a change in Y. And remember, in both of these cases, we're looking at infinitesimal changes. So very, very small changes in X and Y. If we think of some applications in economics, we can think of the savings function, which is a function of income and the interest rate. We know that when income changes, it will change savings, but we also know that when the interest rate changes, it will also change savings. So if we want to work out the total effect on S when income and interest change at the same time simultaneously, we need to find the total differential, as we did on the previous slide. So the total differential, ds, we would need to partially differentiate this function here with respect to y. Okay, and there would be the partial derivative. This here is looking at the rate at which savings change when there's an infinitesimal change in y. So here we would be looking at the marginal propensity to save, times by dy, plus here we would need to calculate the partial derivative of savings, the savings function here, with respect to I, and we would include that over here, times by di. So this total differential here would add together the change in savings due to a change in income and the change in savings due to a change in the interest rate. Another economic example, if we have a utility function, and utility is a function of consumption of various goods, okay, however many there are, up till n goods. And if we wanted to calculate a change in utility, if we wanted to work out the differential du, we would need to add together the change in utility from changing the consumption of all of these goods. Okay, so for example here, we're looking at the change in utility when consumption of X1 changes, and this here would be marginal utility of X1, and we would calculate this value by partially differentiating this utility function with respect to X1. All right, times by dx1, an infinitesimal change in X1, plus this partial derivative here, partially differentiating this function with respect to X2. This here would be the marginal utility of good X2, okay, times by an infinitesimal change in X2, consumption of X2. All right, so each partial derivative, as I mentioned, these are the marginal utilities from consuming each of these goods. All right, and we need to add all of these up in order to calculate the total change in utility.